This is AP Calculus 510, Introduction to Optimization Problems. In this section, you're going to be asked to maximize or minimize a value associated with your problem. You're going to be finding maximum area, minimum cost, maximum profit, and things like that. For example 1, Wanda wants to put fencing around a rectangular garden. One side of the garden is her house. She has 72 feet of fencing for the other 3 sides. Find the maximum area of the garden. So I'm going to take the important information and put it on my whiteboard, and then we'll solve the problem from there.
So I put the important information up here for you. First thing you need to understand is to do this, we have 72 feet of fencing, and we're using 72 feet of fencing to do 3 sides of our garden fence. The house will act as the 4th side. So we really only need 3 dimensions that we're worried about. Now, I've got that the length is the same for both of these. I've made those X, and that the width is Y. Now, it is possible that they may all be the same. It just depends on the problem and what you've been asked to find. But we don't know for sure whether they're going to be the same or not. That's why I need different variables. Now, we know the length will be the same on both sides because it's a rectangle, but we don't know what this side is. That's why I'm using a different variable there. It's kind of common sense. They're asking us to find the maximum area. Now, with optimization problems, where you're finding maximum area, minimum costs, things like that, you're going to have 2 equations. You're going to have a primary equation and you're going to have a secondary equation. Your primary equation is going to be the equation associated with what you're trying to maximize or minimize. So I'm trying to maximize area, so my primary equation is going to be my area formula, area equals length times width. My secondary equation in this one, because they gave us that we have 72 feet of fencing, my secondary equation is going to be the perimeter equation associated with this problem. Now, if you think about that, we have 72 feet of fencing to do these 3 sides, and 2 of the sides are the same. So wouldn't that mean that 2x plus y is equal to 72? That's my secondary equation. 2x plus y equals 72. Now, in order to do these problems, we're really only allowed to have 1 variable. So what we have to do, using the secondary equation, is get everything in terms of 1 variable. Now, usually we make that x. So what I'm going to do is over here, I'm going to get y by itself, and I'm going to solve that and have y equals 72 minus 2x. So that's what y is equal here. That's what y will equal here. So now I can go to my primary equation and plug the information in. My area is going to be equal to length times width. So that's x times y. And now that I know what y is, I can plug y in here. So area equals x times y is 72 minus 2x. Now I have my equation with 1 variable. I can maximize this problem by finding the derivative, getting my critical values, and testing to make sure they are a maximum. If you have more than 1, the maximum would be the highest. Usually for these though, they're very straightforward. You will have 1 answer, it will be a maximum, and you'll be done. So if you're looking at this, we've got the area here is 72x minus 2x squared. So a prime is 72 minus 4x. If I set that equal to 0, I'll have 72 equals 4x. And then if I divide 72 by 4, I end up with x equals 18. So if x equals 18, if you remember back when you were doing these problems in Algebra 2 or Pre-Calculus, when x equals 18, your x value represents the dimensions, okay? So if x is 18, that means we can plug 18 in here to find y. So y will be 72 minus 36. So y will be 36. So what this means is our dimensions of the fencing or the fenced-in area or the garden is going to be 18 by 36. So it's 18 feet by 36 feet. And so the max area is going to be what we get when we multiply those 2 things together. So my max area is going to be 648 feet squared.
A large open-top bin has a square base. The base costs $9 per square foot and all sides cost $11 per square foot. The volume of the box must be 120 feet cubed. Find the dimensions that maximize the cost of the box.
I've got all the important information for the second problem here. The cost of the base material is $9 per square foot. The cost for each of the sides is $11 per square foot. My volume of my entire box has to be 120 feet cubed. I have a square base, so they told me the base was squared. So I'm going to make this X, and I'm going to make my height equal Y. And we're trying to find the minimum cost. So we're minimizing cost. So my volume formula is going to be my secondary equation, because we're not maximizing or minimizing volume. We're using the volume formula to minimize cost. My cost formula will be my primary equation. This one is a little bit more involved. It's got a little bit more detail with the setup, but once you get the setup, it's pretty easy. You take the derivative, set it equal to 0, and find your maximum or minimum. So my minimum cost for my secondary equation, I know that volume is length times width times height. So if I plug into that, I know my volume has to be 120 feet cubed. My length is X, my width is X. So I've got X squared times my height, which is Y. Okay? I can get Y by itself very easily. That's 120 over X squared. That's the purpose of having my secondary equation. Now I'm going to use my primary equation, the cost equation, and then plug in Y, whatever Y is, I'm going to plug in 120 over X squared. So first I need to think about my cost. Now they told us that this was an open top. We don't have a cost for the top of the box, but we do have a cost for the bottom. Now if you think about that, here's the bottom of the box right here, okay? If you think about the bottom of the box, the area of that box would be X squared, okay? Now, the cost of the base of the box, and since there's only one of them, it's going to be $9 times X squared. So for my primary equation, my cost formula, I have $9 times X squared. Since we don't have the top, we only need one of those. For my sides, if you think about the dimensions of the sides, this is Y, this is X. So we've got XY for the area of that side, and every one of these is going to be XY, if you look at it, okay? So how many of those do we have? Well, we've got 4 of them, so we've got 4 times XY for the area of the sides, and we know that the sides are going to cost $11 per square foot. So this is the square footage of each side. We know each of those is going to cost $11. If we add both of these together, we will have our equation. Now, the problem with this is we have 2 variables. We need 1 variable. So I'm going to clean this up a little bit. I've got 44x times y, and my y is 120 over x squared. So my cost is 9x squared plus 5,280 over x. Remember, this x will be on top. It'll cancel with one of those. The next thing I have to do is take the derivative. If I take the derivative of this, c prime, well, this is pretty simple. It's just going to be 18x. For this, I really need to rewrite that as 5,280x to the negative 1. That will make the derivative very simple to take. You don't have to use the quotient rule that way. So if I do c prime, take the derivative, I've got 18x minus 5,280x to the negative 2. So I have c prime equals 18x minus 5,280 over x squared. I set that equal to 0. Now, think about this. My critical numbers are anywhere that this function is equal to 0 or it's undefined. Now, if you think about the undefined part, if we set x squared equal to 0, we're going to get x equals 0. Now, if you think about that being a critical number, and it is a critical number of the equation, there's nothing wrong with that. But if you think about that in terms of, can that be our answer? Well, can you have a length that is 0? If we have a length that is 0, we don't have a box at all. We have a point, because it's not going anywhere, okay? So that critical number will not yield us any answers, so we're gonna throw it out. You can throw out anything that's a length or a cost of 0, you can throw it out. If you have a negative number for a length, you throw that out because you can't have a negative length. So there are some critical numbers that you'll be able to throw out because there's no possible way they could be solutions. And so then for this one, if I set those equal to each other, I've got 18x equals 5,280 over x squared. I'm going to multiply that over 18x cubed equals 5,280. When I divide this by 18, I end up with 880 over 3, and then I take the cube root of that. So the cube root of both sides gives me the cube root of 880 over 3, which gives me an x equals 6.644 feet. So my x value is 6.644. My y value will be, and to get my y value, I plug that into this right here. My y value is 2.718. So we've got the dimensions of 6.644 feet by 2.718 feet. Those are the dimensions that will minimize our cost for this function.
Problem number 3, find the point on the line y equals 2x plus 5 that is closest to the origin. Now considering that problem, look, here's the graph of y equals 2x plus 5, and we're trying to find the point on this line that is the closest to the origin. We're going to use the distance formula for this from geometry. Remember, the distance formula is distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And we will use that distance formula to try and generate an ordered pair that is closest to the origin from this red line.
So if I'm trying to minimize the distance between the line y equals 2x plus 5 and the origin, I'm going to use the distance formula. And if we know that the origin is the point 0, 0, what I can do is I can plug that 0, 0 point in for the x1, y1 ordered pair. And if I do that, if you think about that, this is going to be 0, this is going to be 0. So that's just going to leave me with d equals the square root of x squared plus y squared. I can drop the x2 and y2, that little 2, because by plugging the origin in, I only have one point left, so I have an x squared, y squared. So this becomes my primary equation. The primary equation is the one that we're going to use to minimize that distance. And so then, if you think about that, I have a primary equation here. My secondary equation will be the equation of the line. And so I can take this equation of the line, since I know that that 2x plus 5 is equal to y, and I can just substitute it in here. So my distance is equal to the square root of x squared plus 2x plus 5 squared. Then it's just a matter of simplifying that information. So d equals the square root of x squared plus 4x squared plus 20x plus 25. Giving me a final equation that needs to be minimized. My primary equation would be d equals the square root of 5x squared plus 20x plus 25. Then we know that if we're going to minimize this equation, we have to take the derivative. So if I take the derivative, that means I'm going to have to use the chain rule, which would give me a 1/2 times 5x squared plus 20x plus 25. We keep the inside the same. Take that now to a negative 1/2. And then we take the derivative of the inside, which would be 10x plus 20. So to simplify that a little bit, my d prime is going to be, I've got a 10x plus 20 on top, and then a 2 times the square root of 5x squared plus 20x plus 25 on the denominator. The next thing I do is I'm going to find the critical values for that derivative. If I set that equal to 0, I will find the critical values. And remember, the critical values are where the derivative equals 0 or where the derivative is undefined. So if I set the numerator equal to 0, I will have x equals -2. If I set the denominator equal to 0, the 2 cancels out, it goes to the other side. If I square both sides, it's not going to be a square root anymore. If I distribute out a 5 and divide it over, the 5 will be gone. So what I have left is the x squared plus 4x plus 5 equals 0. And then I need to try to factor this trinomial. Are there factors of 5 that add to give you 4? There are not, so it's not factorable. So at this point I would go to my calculator, go to the polynomial solver, and solve that. And when I do that, it gives me imaginary roots. So there are no critical values that come from the denominator. So that means our only critical value is x equals -2. And so we can assume that that is the minimum length. And so if x is -2, the ordered pair that is closest on the line to the origin would be the ordered pair -2. And if I plug -2 in here, I would get 1. So -2, 1. Now another thing you can do with this, just dealing with the calculus, is if this is a critical value, we can say, okay, I've got the critical value of -2. I can set up the interval -infinity to -2, -2 to infinity. I can pick a value, so like I could pick -3 and maybe a 0. I could plug that into my derivative. When I plug that into the derivative, on the top, that would be a negative. The bottom would be a positive, leaving me with a negative here. And if I plug 0 in, I would have a positive on top and a positive on the bottom, leaving me with a positive. And that shows me the direction, would give me the direction of a minimum. And this is, in fact, minimizing the distance. You could do this chart every time you find a maximum or minimum, or you have an applied maximum or minimum problem, but almost always we will only have one value, and it is safe to assume that that is your minimum or your maximum, depending on what they're asking you to find. But you do need to understand that if you set it up this way and test for the relative minimums or maximums here, it will show you what you're actually trying to find.